everyone, welcome to Vedantu's NCERT Solutions class 11 and 12 where we discuss NCERT exercises of different chapters by different teachers. So today I am here to give you the class 11 topic chemical bonding and molecular structure exercise questions. So let's start with the question number 1. Explain the formation of a chemical bond. So for the formation of a chemical bond, we know that is the attractive force. What is a chemical bond? We can simply say that it is the attractive force that held the constituents of a compound, right? That is an attractive force that hold the constituents of a compound. Okay, that is actually the attractive force that hold this constituents of a compound. Okay, so we have lots of theories like valence shell electron pair repulsion theory, we have valence bond theory, we have molecular orbital theory that give us the theories of the formation of a chemical bond. Actually, we believe that inert gases or noble gases are inert because they are highly stable. Right? So the bond formation, what is the criteria of a bond formation is to become stable. Okay, so they have to achieve that inert gas configuration. So for that they can lose their electron, they can share their electron by any means, they can form a chemical bond. So based on that, we have two types of chemical bonds. We can say that is ionic bond. Broadly I am classifying as ionic bond and covalent bond. In ionic bond, losing or gaining of electron is happening, whereas in covalent bond, sharing of electrons are happening. Okay, in covalent bond, we have different types of bonds as well. Okay, so the idea of a chemical bond is that is the attractive force that hold the constituents of a compound together. Okay, yes, and we have the theories like VSEPR theory, valence bond theory, molecular orbital theory that all explain about the formation of a chemical compound. And you have to understand that for the bond formation, the criteria of the bond formation is to become stable, and they can attain the stability by getting the inert gas configuration. Okay, yes, I hope you got or understand the answer for this question. So here we are with the second exercise question from that chapter. Let's see this. Write Lewis dot symbol for the atoms of the following elements. So we have to know what is a Lewis dot symbol. Lewis dot symbol is nothing but where we represent the elements based on their number of valence electrons. So for example, we can say for magnesium, its electronic configuration is actually 2, 8, 2, where we can represent magnesium by Lewis symbol as like this. Okay, because that is the number of valence electron which is present for magnesium. And coming into sodium, it will be what? It will be 2, 8, 1. So we can write it like not Mg, that is Na. Yes, right, Na with 1 electron. And coming into boron, we know its electronic configuration will be 2, 3, that is fifth atomic number is 5 for it. So we can write it like what? That will be 1, 2 and 3. Oxygen coming the 16th group element. So it will be having 6 electrons in its outermost shell. 6 electrons in its outermost shell. That is 2, 8, 6 actually. So I'll be writing oxygen like 2, 4 and 6. Coming into nitrogen, which is the 15th group elements, and it will be having 5 electrons in its outermost shell. So I can write it like 2, 4, 5. Right? And bromine is the 17th group element, so it must be having 7 electrons in its outermost shell. So it will be like what? Bromine 2, 4, 6 and 7. This is how we can represent these elements by Lewis dot symbol. Okay, very easy. You have to show the number of valence electrons along with the element. Okay, so that's about this question. I hope you got this one. If you have any doubt, please let me know. Write the Lewis symbol for the following atoms and ions. So first we have sulfur, which is again a 16th group element, right? It's a 16th group element. So sulfur will be having 6 electrons in its outermost shell. Am I right? Yes. Okay. When it comes to S2 minus, the negative symbol indicates gaining of electron. So 2 negative means it have gained 2 electrons. So we will be having 8 electrons in the outermost shell. So we can write it like S2 minus like this. Okay. Yes. Now coming into aluminium. Aluminium, we know it's a 13th group element. So it will be having 3 electrons in its outermost shell. But when it comes to Al3+, we know the positive charge implies losing of electron. So 3+ means it have lose its 3 electrons. So we can write what? No electrons will be there in the outermost orbital. So I am writing it like Al3+, just like that. Okay, now coming into hydrogen, we know hydrogen will be having only 1 electron, and coming into H minus, it have gained 1 more electron. So we can write it like this, H minus. Yes? Draw the Lewis structures for the following molecules and ions. Okay, so we have to write the Lewis, like before we had 3 questions. All of the question was to draw the Lewis structures, and which is very important topic in this chapter. Okay, yeah. So H2S, we know for hydrogen it need 1 more electron to become stable, and for sulfur it need 2 electron to become stable. So we can say for hydrogen it need 1 electron, and for sulfur also it need 1 electron. So what can they do? They can share their electrons so that they can get 2 electrons. So we can write it like sulfur 2, 4 and 6. I am writing it like this. And it have shared its one of its electron with the electron of hydrogen. So we can write it like this. This thing I'll be, yes, please let me change it. Sulfur, 1 electron pair here, another electron pair here, and hydrogen here. It have shared their electrons. So now hydrogen have 2 electrons, sulfur have 2, 4, 6 and 8 electrons. All of them are stable now. Right? And coming into SiCl4, silicon is a 14th group element. It need 4 electron. Chlorine again need 4 electron. So they will be sharing their 4 electrons each other. So we can write it like 1 electron here, 1 here, 1 here, 1 here. Chlorine here, 1 electron, here 1 electron, chlorine here, 1 electron, another chlorine here, 1 electron. They will be making bond like this. Got it? So now silicon have 2, 4, 6, 8 electrons. Chlorine have here 1, 2, 3. 1, 2, 3. 1, 2, 3. So 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Now here hydrogen, I have to write 1 more electron here. Okay. Yes? Okay, I hope you got this one. Okay, for hydrogen there is no need of that electron. Only 1 electron hydrogen have, right? Yes. Okay. Next one we have is BeF2, where we have, in case of Be, we have only 2 electrons. So it need what? 2 more electrons. So it will be sharing it with fluorine. Yes, now fluorine have this electron. So 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 8. Now beryllium have 2 and 4. Yes? Okay. Now HCOOH. We know for carbon, CO3 2 minus. CO3 2 minus, we know each carbon need 4 electrons and oxygen need 2 electrons. Each oxygen need 2 electrons. So it is given that the CO3 have gained 2 electrons. Right? Yes. So we can write carbon have formed a double bond with one of the oxygen. Okay? And single bond with another oxygen, and another oxygen single bond. Okay, now we know what carbon's octet is complete, but for this oxygen it's not there, right? Yes, it's just like this. Correct. 1 electron here, 2, 4, 5, because the 6th electron have made this bond. Okay, now we know what there is 2 minus. So 1 minus will be coming here with an electron. Another minus will be coming here with an electron. So the structure of CO3 2 minus will be like this. Okay, yes, now you look at this oxygen 2, 4, 6, 8. This oxygen 2, 4, 6, 8, because it have given its 2 electrons to share with carbon. Clear? So for carbon 2, 4, 6, 8. For this oxygen 2, 4, 6, 8. Got it? Now HCOOH. So for carbon again we need how much? 4 bonds. So first oxygen will form a double bond, and 1 electron will be shared by 1 hydrogen. 1 electron will be shared with another hydrogen. Then again another oxygen is coming and sharing its 1 electron. Okay, now this oxygen need 1 more bond, so that will be with 1 electron from hydrogen. So you just look at this carbon 2 4 6 8, oxygen 2 4 6 8, hydrogen 2, and again coming into this oxygen 2 4 6 8, this hydrogen 2, all of them are stable, right? So this will be the Lewis structure of these following compounds and ions. Okay, define the octet rule, write the significance and limitation. So octet rule is also called the electronic theory of chemical bonding. It was given by the two scientists Lewis and Kossel. Lewis and Kossel have given this theory. So according to this theory, atoms can combine either by transferring their electron with each other or by sharing their electron in order to attain what? The nearest noble gas configuration and become stable. That is the particular idea of this octet rule that we can say. Okay, that means atoms can combine either by transferring of electrons with each other or by sharing of electrons to attain the nearest noble gas configuration. So the idea is that if we attain the nearest noble gas configuration, it will become stable. That was the idea, and for most of the element it was working. For most of the compounds it was working. Okay, but there are some limitations. So the first limitation, we can say that by octet rule they couldn't say the shape and stability of the molecule. They couldn't talk about the shape and stability of the molecule, why they are stable and what is their shape. They cannot give the information about that. Okay, and the next limitation that we can say is shape and stability they couldn't say. Okay, next one we can say it was based on the inertness of noble gas, right? Inertness of noble gas. But later on we have identified that some of the noble gases are reactive and they are forming compounds like HCF2 and KRF2. So xenon and krypton, they are reactive and they are forming some compounds. If they were stable, they would not do this, right? Yes, so we can say the inertness of noble gases, we cannot take that criteria to say about chemical bond formation. Okay, and the third one, what does that mention is that they will attain the nearest noble gas configuration, right? But that is not in the case of some of the compounds where we have more than 8 electrons in their valence electrons. Like we have SF6. In SF6 there are 12 electrons in the outermost shell. As you can see here, SF6 structure will be like this, right? It have how many electrons? 2 4 6 8 10 and 12 electrons are present. If you look at PCl5, what is the structure of PCl5? Cl, 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 Cl. Okay, how many electrons are there? 10 electrons are there. So we can say what? For SF6 and PCl5, this is not following that octet rule. And again, we can have another electrons like NO, where when NO, we can say that is an odd electron system. That is an odd electron system in case of NO. Okay, yes, so we can say what? We can say what? It is again another criteria where we can have only odd electrons on the nitrogen atom. Again, we can take NO2. Okay, yes, NO2 again, it's a odd electron system that is coming for nitrogen. Clear? Yes, and again we can have another electrons where there is less than what? Less than octet is present. For example, just now we took the this example for the previous question, that is BeH2, where they have only 4 electrons. It is less than what? Less than what? 8 electrons. Again I can take AlCl3, only 6 electrons are present. Again they are what? Stable. I hope you got this. Right? So these are the limitations of octet rule. I hope you understood the answer for this question. Write the favorable factors for the formation of ionic bond. So we know how the ionic bonds are formed. Ionic bonds are formed by the transfer of electrons between the atoms, right? Between the atoms. So in that we can say one of the atom will be losing its electron and the other one will be gaining its electron. So the easiness to lose the electron and the easiness to gain the electrons, these are the main properties on which the ionic bond formation can depend on, right? And also ionic bonds or mostly they will form what? The lattice structure. So their lattice enthalpy also must be what? Lattice enthalpy also must be high. Clear? Yes, so we can say for ionic bond, transfer of electron between the atoms is happening and their lattice enthalpy can be taken into an account. Okay, so we can say for losing of electron, which is the amount of energy which is required to lose an electron, that is ionization enthalpy, that amount of energy must be low so that atom can lose its electron easily. So we can say it must have low ionization enthalpy for the metal or for the positive ion. And for gaining of electron, the electron gain enthalpy must be more negative. High electron gain enthalpy. High electron gain enthalpy must be there. It must be more negative, and coming into lattice enthalpy, it must have what? High lattice enthalpy. So during the formation of the lattice, they have to release more energy. So that is what is high lattice enthalpy. Okay, so these are the main three criteria on which the ionic bond formation depend upon. Discuss the shape of the following molecules using VSEPR theory. We know valence shell electron pair repulsion theory. So on that, what we will be considering is which is the central atom and what is its number of valence electron, how many bond it have made, and based on that we will predict the geometry of that molecule. So let's do that. So BeCl2, from that we can say Be is the central atom and Be is having two outermost electron and two of them have made bond with chlorine. So we can say its structure will be or it is of type AB2, so that must be linear in geometry, right? Yes, now coming into BCl3, we know around B we have how many electrons? 3 electrons, and 3 of them have made bond with chlorine. So we can say their shape will be like AB3, right? AB3 without any lone pair. So we can say it is of type AB3. So it will be having a structure trigonal planar. What will be the shape? Trigonal planar. Then we have SiCl4. What is that? SiCl4, where silicon is having 4 electrons in its outermost shell and 4 bonds are made here. So we can say it is of type AB4 and it must be tetrahedral in geometry. So the structure will be like this. Cl, Cl, Cl and Cl here. Okay, so that is tetrahedral. Then again we have AsF5, where arsenic have 5 electrons in its outermost shell and those 5 electrons are making bond with fluorine here. So it will be of type what? Yes, I can write it like this. Okay, so one fluorine here, 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 and it is of type AB5, and its geometry we can say it is trigonal bipyramidal. What is that? Trigonal bipyramidal. Then we have H2S, where the central atom is sulfur and the sulfur is having 6 electrons in its outermost shell and 2 of them have made bond with hydrogen, right? Yes, so we can say or we can write that structure as 2 of them have made bond with hydrogen. So the 2 lone pairs are also here. So it is of type AB2E2. So it will be having a shape of bent shape or inverted V shape, we can say. Clear? I hope you got this. It is of type AB2E2. That is why it have the shape of bent, because 2 lone pairs are there. In VSEPR theory, the main criteria that we look for is the lone pair. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. Right? Then again PH3 is the next one. In PH3, this phosphorus is having 5 electrons in its outermost shell and 3 of them have made bond. So we can write that will be like this, and one lone pair will be here. So one hydrogen here, another hydrogen here, another hydrogen there. So it is of the formula AB3E and its structure will be trigonal pyramidal. What is that? Trigonal pyramidal will be the shape of PH3, because PH3 is having this phosphorus is the central atom. Phosphorus having 5 electrons in outermost shell, only 3 of them have made bond with hydrogen and 2 electrons or 1 lone pair is missing there. Got it? Yes, so according to VSEPR model, we can explain the geometry of these molecules like this. I hope you understood the answer for this question. Although geometries of ammonia and water molecules are distorted tetrahedral, the bond angle in water is less than that of ammonia. Discuss. So, we can just find the structures or the geometry of ammonia and water first. So let's see ammonia. Ammonia is having the nitrogen as a central atom, where nitrogen have 5 electrons in its outermost orbit, right? Yes. And among the 5, 3 of them have made bond with hydrogen. So the structure will be like this. Hydrogen, 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 and 1 lone pair here. Actually, it is a 4 electron pair system. 4 electron pair system. Among them, 3 of them are bond pair and 1 lone pair is there. Right, and that is why it got the structure trigonal pyramidal, right? Yes, here the repulsion is between 1 lone pair and 3 bond pairs. 1 lone pair and 3 bond pair repulsion is happening in case of ammonia. Now, when it comes to water molecule, oxygen is the central atom, and here we know oxygen is having 6 electrons in its outermost orbit and only 2 of them have made bond. So, their structure will be like H here, 1 lone pair here, another lone pair here. So, again, it is a 4 electron pair system, but among that, we have 2 bond pairs and 2 lone pairs. That is why they got the shape bent. Okay, so since all of them are having 4 electron pair system, we can say they are distorted tetrahedral structure. That was supposed to be tetrahedral, but since they have lone pairs, their shape got changed to trigonal pyramidal and bent respectively. Right? Yes. Now, if you look at this, you can see here they have 2 lone pair, 2 bond pair repulsion. So, if you compare the 2 repulsions, this repulsion is more than the repulsion which is present in ammonia. So, these 2 lone pairs will repel the 2 bond pairs towards inside, so that their bond angle is decreasing, but there is not that much lone pair present in ammonia. As I mentioned in the previous question number 4, we have mentioned that what lone pair repulsion is greater than lone pair bond pair, which is greater than bond pair. So there is more number of lone pair present in water. That is why their bond angle is less than that of ammonia, even though both of them are distorted tetrahedral structures. Okay. How would you express the bond strength in terms of bond order? So first you have to know what is a bond order. So bond order is the number of bonds between 2 atoms in a molecule, right? That is the number of bonds formed by 2 atoms between 2 atoms in the molecule, right? And as the bond order increases, number of bonds increases, their extent of bonding increases. Right? And as the extent of bonding increases, bond strength increases, their bond energy also increases. So we can say bond order and bond strength are directly proportional. As bond order increases, bond strength increases and bond energy also increases. Extent of bonding also increases. Yes? Simple as it is. I hope you understood the answer for this question. Define the bond length. So, simply saying bond length is the equilibrium distance between the nuclei of 2 bonding atoms. Okay, so if I have an ionic compound where we have the cation and the anion, the distance between the nuclei of the cation and anion, that we can say as the bond length here. For a covalent molecule, they are sharing their electrons, and the distance between the nuclei of these two atoms, we can say this is the bond length for the covalent bond. Okay. Yes, and we can measure them by using the unit Armstrong and picometer. These are the unit that we are using while measuring them. That is 10 power minus 10 and 10 power minus 12. And we can measure the bond length of a bond by using X-ray diffraction or electron diffraction methods. Okay. Yes. Explain the important aspect of the resonance with respect to CO3 2- ion. So we have mentioned the structure of these the same ion in the previous question, where we have came to know that the structure of CO3 2- will be like this. I am mentioning the number of lone pairs also here. Okay, this is one of the negative charge and another negative charge. Okay, yes. So this negative charge can go to this oxygen, and this oxygen can get a double bond. That is another way in which we can represent the same molecule. Am I right? Where we will be having minus here, 2 lone pairs here. Another way by which I can represent this is this double bond is coming here and the negative is going here, right? So we'll get the structure like O minus here, double bond here, O minus here. Got it? So in these three structures, the nuclei is remaining the same. The position of nuclei is the same. That is the particular criteria of a resonance. Okay, the nucleus is not changing there. Okay, and all of them are having almost equal energy. Almost them have almost equal energy, right? Okay, and all these structures we are having same number of unpaired electrons. Same number of unpaired electrons are present in every structures, but their positions are different. That is the main difference in these structures. Okay, yes. So these are the three important points that we can take from this resonance structure of CO3 2- ion. Okay. H3PO3 can be represented by structure 1 and 2 as shown below. Can these two structures be taken as the canonical forms of the resonance hybrid representing H3PO3? If not, give the reason for the same. Okay, so we know what in the case of this canonical forms or resonance form, we know that the nucleus must not be changing their position. It must be the same in every structure. Their energy must be same. Number of unpaired electrons must be same. If you look at here, the hydrogen is present here. And if you look at the second one, the hydrogen is present with oxygen, or the position of atom got changed. Position of atom got changed in the second picture. So because of which we cannot consider this as the canonical forms of H3PO3, since the position of atom got changed. Yes, I hope you understood the answer for this question. Write the resonance structures of SO3, NO2 and NO3-. So for first one, SO3, we can write the structure of SO3 like this. It will be having a double bonded oxygen here, single bond oxygen with 3 lone pairs here and 2 lone pairs here, 3 here. Okay, actually sulfur have donated its 2 electrons for the oxygen to make bond for these two. Okay, so there is a possibility of shifting of this lone pair to this bond, and this double bond will be moving here to maintain the octet of sulfur. So what will happen? This bond will shift here and this bond will go here. So what is the next structure? It will be like this. Here the double bond, here again 3 electrons. Again there is a chance for the electrons of the next sulfur to move from here to here and make a double bond here, so that this double bond will go this side. Okay, so the next structure will be like single bond O, and here again single bond 1, 2, 3. Okay, yes, then again double bond with 2 lone pairs. This is the resonance structure of SO3. And for NO2, the shape or the structure is like this. Okay, yes, NO2, the shape of NO2 is like this. Okay, so we can write it like what? Here we will be having 2 lone pairs, 2, 4, 6. Okay, so here it can happen like this. Okay, now how it will be? It will be a single bond here with 3 lone pairs and a double bond here. Got it? Yes, so that is how the structure of NO2 will be. And for NO3-, what will be the structure? 1 double bond and 2 single bonds will be here. Okay, yes, now what will happen? This bond, this electron will move here, this bond will go there. Okay, just like SO3 that we have done, the same thing will happen here also. Yes, okay. So here we can write it like what? Here, not oxygen, it is nitrogen. So N here, double bond O, single bond O, single bond O. Okay. Yes, again 6 lone pairs here, 2 here. Okay, again what will happen? This will move here, this will move here. So the double bond is going to each and every positions. Clear? I hope you got this answer. If you have any doubt, please let me know. Use Lewis symbol to show electron transfer between the following atoms to form cations and anions. So we have potassium and sulfur here. So we know for potassium it is 2, 8, 8, 1, or it will be losing its 1 electron since it's a first group element. And for sulfur it is what it is a 16th group element, so it need 2 electrons. So 2 potassium will be forming like K2, and the sulfur with 8 electrons will be there with 2 minus. So K plus 2, K plus will be there, and what? 2 K plus will be there, and S2 minus will be there. That is how the structure of potassium and sulfur ions will be there. Okay. Yes, and for calcium and oxygen, for calcium we know it is 2, 8, 8, 2, and it will lose its 2 electrons and oxygen will take that 2 electrons. So calcium will form Ca2 plus, and for oxygen it will be again 8 electrons with the 2 minus charge. Okay. Yes, and coming into aluminium and nitrogen. Aluminium we know it is 2, 8, 3, and nitrogen it is 2, 5. It needs 3 more electrons and it will give its 3 electrons. So we can write it like Al3 plus will be there, and nitrogen with again 8 electrons with a 3 minus. Yes. Although both carbon dioxide and H2O are triatomic molecules, the shape of H2O molecule is bent while that of carbon dioxide is linear. Explain this on the basis of their dipole moment. So we know for carbon dioxide, it have 2 carbon-oxygen double bonds. And their net dipole moment, we got it like what? We will get it like 0. That is why we can say it will be having a shape of linear shape. Then only it will get that dipole moment. Here it will be like what? This, and here it will be like this. So these two equal and opposite things will cancel and become 0. That is why we can say, since the dipole moment of the carbon dioxide is 0, we can say it will be having a linear shape. But when it comes to our water, what is happening there? They have a net dipole moment. Value. That means they are not linear. Okay, since there is same atom that we have, which is bonded with oxygen, since they are not linear, they are having a net dipole moment. So we are expecting the shape of what a molecule have this bend shape, because here the structure will be like this. So these two will be getting added up and it will be having a particular dipole moment value. So write the significance or applications of dipole moment. So dipole moment, we know when equal and opposite charges are put in a particular distance, there will form a dipole moment. So dipole moment, we can use the dipole moment to predict the nature of a compound. If a compound have a net dipole moment, is there, means we can say they are polar molecule. If net dipole moment is equal to 0, then we can say it is a non-polar molecule. So based on the value of dipole moment, we can identify the nature of the molecule, whether they are a polar molecule or a non-polar molecule. Got it? Yes. And next one, we can say we can just predict the shape of a molecule by knowing its dipole moment. Again, we can find the percentage ionic character of a molecule by knowing its dipole moment. Percentage ionic character also we can calculate by using dipole moment. So these are the significances or applications of dipole moment that we can say. I hope you understood this one. Define electronegativity. How does it differ from electron gain enthalpy? Electronegativity means what? It is the tendency of a bonded atom to attract that shared pair of electron towards itself. What is that? That is the tendency of a bonded atom to attract the shared pair of electron towards itself. Okay, but when it comes to electron gain enthalpy, what is that? Electron gain enthalpy, that is the tendency to attract an outside electron towards itself. Okay, yes, and this is a property of an isolated atom. This is a property of an isolated atom, whereas in case of electronegativity, that is the property of a bonded atom. That is the major difference between them. And electronegativity, they are attracting the shared pair of electron towards itself. When it comes to electron gain enthalpy, it is attracting another outside electron towards itself. Okay, I hope you understood the difference between electronegativity and electron gain enthalpy. If you have any doubt, please let me know. Explain with the help of suitable example polar covalent bond. So polar covalent bond is nothing but we can say that is the type of covalent bond. Yes, covalent bond formed between elements having difference in their electronegativity. So if there is a difference in the electronegativity of the bonding atoms or bonding elements, what will happen? The one which is having more electronegativity, that will try to take that shared pair of electron towards itself. That shared pair of electrons will not be at the center. They will be nearer to the more electronegative element. For example, if we take the bond between hydrogen and fluorine, here fluorine is more electronegative than hydrogen, as we all know, right? So what will happen? The fluorine will try to take these two electrons towards itself so that it will get a slight negative charge and hydrogen will get a slight positive charge. This type of compounds are called what? Polar covalent molecules. Just like that, we can take HCl where chlorine will be getting a slight negative charge and hydrogen will be getting a slight positive charge. Arrange the bonds in the order of increasing ionic character in a molecule. So to increase the ionic character in a molecule, what we need is there must be a difference in electronegativity of the elements. Electronegativity of the element, if there is high difference in electronegativity of the combining atoms, they are more ionic, we can say. So if you look at this, you can see there is lithium and fluorine, whereas lithium is a metal and fluorine is a non-metal with high electronegativity. So we can obviously say lithium fluoride will be having more ionic character than any other compound present here. And we can say the least one will be N2, because it is the same element which is making a bond and it will be a pure covalent bond. There is no electronegativity difference between two nitrogens, right? So LiF will be more, then it will go to K2O, where potassium is highly electropositive and oxygen is highly electronegative. So we can write K2O next. Then we can go to SO2 and ClF3. Among that, the most electronegativity difference is between what? That's between K2O we have written, and we will be having ClF3 next, because each of them are having a quite difference in their electronegativity. Then only we can go to SO2. Again, chlorine and fluorine are like this, and here we have what? Oxygen and sulfur. So if you compare the electronegativity, for fluorine is higher and chlorine is higher, so the difference will be higher for fluorine and chlorine. That is how it is coming as ClF3 here, SO2 here, and the least one will be N2. Okay, so we have asked for the increasing order, so we have to start from N2 less than, the symbol is wrong, so we have to write N2 less than, SO2 less than, ClF3 less than, K2O less than LiF. So this will be the correct order. Yes, I hope you understood the answer for this question. The skeletal structure of CH3COOH is shown below is correct. but some of the bonds are shown incorrectly. Write the correct Lewis structure for the acetic acid. So acetic acid, we know the structure is CH3COOH. So here you can see the first thing that will come to our mind is this thing, because hydrogen will never form a double bond. So we can say the first the correction is here. So we can write for CH3 it must be like this, right? Then we have C, oxygen must be having a double bond here, so it will be double bonded oxygen with 2 lone pairs, right? And again carbon is remaining with one more bond that will be forming with oxygen, and again another one with hydrogen. Now this oxygen will be having 2 more lone pairs here. Carbon will not have the lone pair. This lone pair must go here, and there will be a double bond. This double bond will be coming here. You got this? Yes? No doubts, I guess. So that's the answer for this 20th, the half of the question that we have completed by now. So yes, that's about it. If you have any doubt, please let me know. Apart from the tetrahedral geometry, another possible geometry of CH4 is square planar with the 4 hydrogen atom at the corners of a square and the carbon atom at its center. Explain why CH4 is not square planar. So here the central atom we have is carbon, and we know its like electronic configuration will be 1s2, 2s2, 2p2, right? And we can write it like what I am writing, 1s, 2s and 2p, right? So 1s2, 2s2, 2p2. This is the electronic configuration in ground state. When we go to this excited state, it will be how it will be. That's the last electron, or the outermost shell will be, the electron will be going into this one. So it will be like 1s2 like this only, and from 2s to 2p electrons will be jumping. So it will be like 1, 2, 3 and 4. Now what will happen to this 4 hybridized orbitals? Hydrogen will be coming and donating its electrons so that it will get paired like this. Okay, that is why it is getting what, sp3 hybridization or the tetrahedral shape. And for square planar, we know for square planar their hybridization is dsp2, and we know what, carbon does not have d orbital to form a dsp2 hybridization. That is why it cannot form what, square planar shape. Okay, and also according to VSEPR theory, the bond angle for square planar is 90 degree, which will increase the bond pair repulsion of that 4 bonds. That also will not suit for the square planar structure of CH4, and their stability will be more in tetrahedral shape. That is why according to VSEPR theory, we can say CH4 can take only tetrahedral shape and not square planar shape, since carbon does not have d orbital to form the hybridization dsp2, also due to high bond pair repulsion with 90 degree bond angle. Yes, I hope you understood the answer for this question. If you have any doubt, please let me know. Explain why BeH2 molecule has a 0 dipole moment, although BeH bonds are polar. Very easy. We know for BeH2 their bond angle is 180, or they are linear in shape. So here when we look at the Be and hydrogen, electronegativity is more for beryllium. So its dipole moment, we can write it like this here, and here it will be like this. We know from least electronegative to high electronegative will be the direction of dipole moment. Since dipole moment is a vector quantity, we have to do the vector addition of this equal and opposite vectors. That is what we are getting here, right? So since they are equal and opposite, we will get the net dipole moment value as 0, even though a single BeH bond is polar. That is due to their linear shape or linear structure, we can say. Linear structure and 180 degree bond angle. So here we have the 23rd question. Which out of NH3 and NF3 has higher dipole moment and why? So I am taking NH3 molecule and its shape will be like this. We know hydrogen here, hydrogen here, hydrogen here. Again for NF3, the same geometry and here we have like this. Okay, so if you look at the NH3, here nitrogen is more electronegative than hydrogen. So the dipole moment of the 3 will be like this, and this lone pair will be going up. That's how for the lone pair we will write the dipole moment. So since all of them are vectors, we will get the vector addition value as like this. Okay, some value will be there for sure. When you look at NF3, here we know for fluorine is more electronegative. So the answer will be, for this 3 bonds, it will be like this. Okay, so it will be giving an addition product like this. Sorry. It will be giving a vector addition product towards downwards like this. And here we have one lone pair also. It will be giving some value towards upwards, and we will be getting a value or as the resultant like this, which will be very small because there is subtraction is happening. Here everything is getting added, so we will get higher value in case of ammonia than in NF3. Okay, that is how ammonia is having higher dipole moment than NF3. What is meant by hybridization of atomic orbitals? Describe the shape of sp, sp2 and sp3 hybridized orbital. Okay, so first question is, what is meant by hybridization? So we know what is hybridization. That is the intermixing of atomic orbitals. Intermixing of atomic orbitals having nearly same energy. To form hybrid orbitals. To form what orbitals? Hybrid orbitals of equivalent energy and identical shape. Okay, so that is the main point here. After hybridization, they will be forming equal number of orbitals having equivalent energy and identical shape. That is what is hybridization. Now we are moving on to the sp hybridization. Means one s and one p orbitals are intermixing, and they will be forming two sp hybridized orbitals. And it is having a linear shape. Now when it comes to sp2 hybridization, 1s and 2p are intermixing and forming 3 sp hybridized orbital, which is directed towards the corners of an equilateral triangle. That is why we call them as trigonal shape. What is that? Trigonal shape. And when it comes to sp3, 1s and 3p orbitals are intermixing and forming 4 sp3 hybridized orbitals, and which is directed towards four corners of a tetrahedron. Okay, yes, so that is what is the hybridization and their particular shapes. Clear? I hope you understood the answer for this question. Describe the change in hybridization of aluminium in the following reaction. So for aluminium, we know it is the 13th element, so it will be 1s2, 2s2, 2p6, 3s2 and 3p1. And for the excited state, I can write it like 1s2, 2s2, 2p6, 3s1, 3p2. Right? It will be like what? 3s and 3p only I am writing, and it will be 1 here, 1 here, 1 here. Okay, so that is what is for what excited one, right? Okay, so now when we move to AlCl4 minus, AlCl4 minus is it got what? And now here you can see it will be chlorine, one chlorine here, another chlorine here, another chlorine here. sp2 hybridization will be coming here. Okay, now when it comes to Al minus, one more electron, it got one more electron, so it will be how much? 3s1 and 3p3. It will be like 1 electron here and 3 electrons here. So when it is forming AlCl4, it will be forming sp3 hybridization. One chlorine coming here, another one, another one, another one. Total 4 chlorine. So here the hybridization is moving from sp2 to sp3. That is how the structure or the hybridization is changing here. Is there any change in the hybridization of boron and nitrogen as a result of the following reaction. So here you can see for BF3 alone, its hybridization will be sp2 hybridization, and for ammonia the hybridization of nitrogen is what? sp3. Okay, because it will be like for boron it will 1s2, 2s2 and 2p1 will be the order. So it will become excited. It will be like 1s here, 2 here. It will be like this. And for ammonia, it will be like what? 1s2, 2s2, 2p2. So it will be for the excited one, it will be like this. Okay. But when it is forming adduct, the BF3 will become from sp2 to sp3. And for ammonia, it will be intact. It will not change. For BF3, the hybridization is changing to sp3. Okay, when it is forming this adduct. Clear? Because one more nitrogen is giving its lone pair to BF3. That is why it is forming what? sp3 hybridized. Draw the diagram showing the formation of a double bond and triple bond between carbon atoms in C2H4 and C2H2 molecule. And we know C2H4 is of CnH2n type and which is an alkene. And we know for alkene their hybridization is sp2 hybridized. Right? And for alkyne it is C2H2 and its hybridization is sp hybridized. Okay, so for C2H4 if you write it, I can say it is sp2 hybridized, right? So it will be like what? sp2 hybridized means it will be like this. One here, another one here. And hydrogens are coming here and one carbon. So here we will be having two carbons and two hydrogens like this, because they are forming what? The p orbital of one carbon, p orbital of another carbon. That means that sp2 hybridized orbitals and the s orbital of hydrogen. That is how they are making their bond, right? And there will be one bond here between them. Okay, so this is the p orbital of carbon and s orbital of hydrogen. Clear? Another p orbital of carbon and s orbital of hydrogen. Another p orbital of carbon and p orbital of carbon. Clear? I will write it like that only. Let me write it like that. Okay. So here we'll be having a p orbital of carbon here and p orbital of carbon here. I'm writing only one double. Okay. Yes, another here we'll be having the p orbital and s orbital. And again another p orbital and s orbital of hydrogen. Here again p orbital and s orbital of hydrogen. P orbital and s orbital of hydrogen. Okay. So that is for how the sigma bonds are formed. Now we know it is only sp2. This free 2pz is there, right? And that free p orbital will be like this. So what will happen? Their lateral overlapping is happening and they are forming one pi bond there. So we will get the shape like what? Two bonds here, two bonds here. Hydrogen, 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 sigma, pi. This is again sigma, 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 sigma. That is how the structure of C2H4 will be by the lateral overlapping of the free 2pz orbital is happening here. But when it comes to C2H2, you can see that what? That is sp hybridized. Sp hybridized means it will be like this. One electron here and another electron here. These two are completely free. So what will happen? One bond will be between the p orbital of two carbon, and one bond here will be here. One bond will be between the p orbital of carbon and s orbital of hydrogen. Here again p orbital of carbon and s orbital of hydrogen. Okay, so these are the sigma bonds which is present. So here you can see this is the sp hybridized, and again another sp hybridized. So three orbitals are making bond here. Here two orbitals. Okay, so the sigma bonds are formed. Now we have this one p orbital and another p orbital. Here again one p orbital and another p orbital. Clear? So what will happen? Each of them will undergo lateral overlapping like this and like this. So what will happen? Two pi bonds will be forming there between them. So it will be like C triple bond C hydrogen, and these bonds are sigma bonds and these two bonds are pi bonds, we can say. Clear? So lateral overlapping of this 2py and 2pz will be happening between the two carbon atoms, and they are forming 2 pi electrons here or 2 pi bonds here. That is how the structure of C2H4 and C2H2 molecules will be. what is the total number of sigma and pi bonds in the following molecule? So we have C2H2 first, and we know the shape of C2H2. It is like what? Triple bond C, single bond hydrogen, single bond hydrogen. We know the single bonds are formed by sigma, and again one of the bond between the two carbon is again sigma, and these two bonds are pi bonds. So we can say here total we will be having 3 sigma and 2 pi bonds. And when it comes to C2H4, it will be like this: hydrogen here, hydrogen, hydrogen, hydrogen. These single bonds are sigma bonds, and here again one sigma and 1 pi. So we can say in total it will be having 5 sigma bonds and 1 pi bond in case of C2H4, and for C2H2 it will be 3 sigma and 2 pi. I hope you understood the concept. If you have any doubt, please let me know. Considering x-axis as the internuclear axis, which of the following will not form a sigma bond, and phi? And why? Okay, so we know s orbital always form only sigma bond. Since they cannot undergo lateral overlapping, they will always form what? Sigma bond. So we can say A will form only sigma bonds. 2s and 2px, since x-axis is the internuclear axis, it will be like this. So they can also form what? Sigma bond only. They cannot undergo lateral overlapping. Again they will form sigma bond. Again when it comes to 1s and 2s, this is the same option which is given. Again this is sigma. 2py, since x is the internuclear axis, 2py I can take it like this. So there is a possibility of lateral overlapping and forming a pi bonds. Clear? So they cannot form what? Sigma bonds, because they are not the internuclear axis. So they will be undergoing lateral overlapping and forming pi bonds. Which hybrid orbitals are used by carbon atoms in the following molecules? That means which hybridization? So CH3, they are having 4 bond pairs. So their hybridization must be sp3 according to BSE-PR theory. Then we have CH3, CH double bond CH2. So here I am giving numbers for each of the carbon 1, 2 and 3. So we know our double bond we are considering as a single bond pair. So we can write for first carbon is sp3 hybridized, 2 and 3. Second and third carbon is forming 3 bonds only. So they are sp2 hybridized. In the case of CH3, CH2OH, CH3, CH2OH, we are again giving numbers to the carbon. This is 1 and 2. 1 and 2 are both are sp3 hybridized, since 4 bond pairs are present for each of them. Okay. Now coming into CH3CHO. CH3CHO, the structure will be like this. I am giving number to each of the carbon. This is first carbon, this is second carbon. Okay. I'm not giving based on the naming, okay? Don't look at it like that. So the first one is what? sp3 hybridized, and the second one having only 3 bond pairs. We can consider it as sp2 hybridized. We have already mentioned the double bond we are considering as a single electron pair. Okay, that is how we are finding the hybridization. Next one, CH3COOH, CH3COOH. Here again we can give the numbers like 1 and 2. Again first one is sp3 hybridized and second one is sp2 hybridized. What do you understand by bond pairs and lone pairs of electrons? Very simple. Illustrate them by giving an example for each type. Okay, so we know what is a bond pair. Bond pairs are the electron pairs which are shared during a bond formation, during a covalent bond formation. During a covalent bond formation, the electron pairs which are shared between 2 atoms, they are called the bonded pairs or shared pairs, we can say. For example, I am taking CH4 as an example. CH4 structure is like this: H, 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 H. One electron of hydrogen, 1 electron of carbon. They are shared and forming this covalent bond. So we can say here we have 4 bond pairs. But when it comes to water, we can say the structure is like this. We will be having 2 electrons which is not participating in the formation of a bond. These 2 electron pairs, we can call them as the lone pair of electron. Lone pairs of electrons are the electron pairs which do not participate in the bond formation or which is not sharing for the bond formation between the atoms. Okay. Distinguish between sigma and pi bonds. Very easy question. For I will make sigma and pi. Okay, so let's put it like this. For sigma bond, we know what here, what type of overlapping is happening here. Coaxial overlapping is happening here. What is happening? Coaxial overlapping. Whereas in case of pi bonds, there is collateral overlapping is happening. What is happening? Collateral overlapping is happening. And when it comes to the bond strength, sigma bond is stronger as compared to pi bond. Pi bond is weaker. Okay, now when we go this to the overlapping, only one lobe of p orbital is getting overlapped. Only one lobe of p orbital is overlapping. For what? Sigma bond formation. We know this only one lobe is getting overlapped, not the other one. But when it comes to pi bond, two lobes of p orbitals are getting overlapped. As you can see here, this side and this side, two lobes are overlapping. Clear? And the last one we can say for the sigma bond is their electron cloud is symmetrical. Electron cloud formation is symmetrical and it is along the internuclear axis. But when it comes to pi bond, their electron cloud is not symmetrical. It is not symmetrical. So these are the major differences between sigma and pi bonds, we can say. Explain the formation of H2 molecule on the basis of valence bond theory. On the basis of valence bond theory, they have asked us to explain the formation of H2 molecule. So I am taking two different nucleus, HA and HB, two different hydrogen atoms. So we know what they will be approaching each other. HA and HB are approaching each other. So what will happen? In HA there is a nucleus Na and there is an electron Ea. And in HB there is their nucleus Nb and their electron Eb. You know the repulsion force will be between them. That is the repulsion force. And between the electrons again there will be repulsion force. Okay. And we can say between Na and Eb there is what? There is attractive force. Right? And between Ea and Nb there is again another attractive force. Even though the number of attractive and repulsive forces are the same, attractive force is more than their repulsive force. So that what will happen? They will keep on approaching together. When they keep on approaching together, their potential energy will get decreased. And at some point the attractive force will become equal to the repulsive force, and at that point in time what will happen? They will form that bond and their energy will be lesser. So they will form a stable bond formation will be happening between the HA and HB. That is how the formation of H2 is happening according to valence bond theory, we can say. Okay. Yes, simply I am saying it like this. So here we are with the 34th question of our NCERT exercise. Write the important conditions required for the linear combination of atomic orbitals to form a molecular orbital. Very simple. And the overlapping orbitals or the intermixing orbitals must have nearly same energy. Like we can overlap 1s and 1s. 1s, 2s overlapping is not possible since there is a difference in their energy. Okay, and again overlapping orbitals must have proper orientation. What does it have? Proper orientations for maximum overlapping. As you know, if I am taking Px and Py, okay, I am taking this as Py and this as Px. What will happen? They can't overlap. So they must have proper orientation for the maximum overlapping. Clear? I hope you got this. They must have proper orientation for maximum overlapping. Yes? And the next one, last and the final one, which is needed for the linear combination of atomic orbital is the extent of overlapping must be maximum. Extent of overlapping must be maximum. Yes, so these are the three conditions for linear combination of atomic orbitals to form their molecular orbital. Use molecular orbital theory to explain why Be2 molecule does not exist. So we know beryllium is hydrogen, helium, lithium, beryllium is fourth element in the periodic table. So it will be 1s2, 2s2. So for Be2 total we will be having 8 electrons. So according to molecular orbital theory, we can write its molecular orbital electronic configuration as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. This is how it will be looking like. And we know according to the molecular orbital theory, we have the equation for bond order, which is equal to half into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. So if you look at this, number of electrons in bonding molecular orbital and number of electrons in anti-bonding molecular orbital, you can see it like what? Half into number of electrons in bonding molecular orbital 4 and anti-bonding again 4. So we will get the bond order as 0. If bond order is 0, that means what? Between the two beryllium there is no bond. That means Be2 does not exist. I hope you understood the answer for this question. Compare the relative stability of the following species and indicate their magnetic properties. Okay, so for actually we have to find the bond order. That's how we can say the stability and magnetic property. Like we have to write the molecular orbital electronic configuration. Simple. Okay, so for O2 we have 16 electrons, so we can write it what? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2p x2 equal to pi 2p y2. 2, 4, 6, 8, 10, 12, 14. Then we'll be having pi star 2p x1 equal to pi star 2p y1. That is how it will be becoming 16 electrons. Clear? Yes, I hope you understood this thing, because sigma 2pz will come here as the number of electrons are greater than 14. Yes? Okay. So here the bond order. Here we can write the bond order of O2. Bond order will be half into number of electrons in the bonding molecular orbital will be 2, 4, 6, 8, 10. 10 minus 2, 4, 6. It will be 2. Okay. Yes, and it is paramagnetic. And it is paramagnetic since there is presence of unpaired electrons are there. Now when it comes to O2 plus means 15 electrons. So here the only difference will be, we will be having only 2px1. Okay, so it will be like sigma 1s2, sigma star 1s2, sigma 2s2 less than sigma star 2s2, sigma 2pz2 less than pi 2px2 equal to pi 2py2 less than pi star 2px1 equal to pi star 2py0. Okay, here the bond order that we can write it like half into 10 minus 5. 10 minus 5 is 5. 5 by 2, 2.5. Clear? Yes, I hope you understood this one. This is also again paramagnetic. Yes, next one O2 minus. O2 minus, we will be having it like 17 electrons. For 17 electron, we can write it like what? Sigma 1s2 less than sigma star 1s2. Sigma 2s2 less than sigma star 2s2. Then we have what? Sigma 2pz2 less than pi 2px2 equal to pi 2py2 less than pi star 2px2 equal to pi star 2py1. Okay, because only one electron got added. So bond order will be equal to half into 10 minus 7, which is 3 by 2, which is equal to 1.5. And again it is paramagnetic because one unpaired electron is present. Now moving on to O2 2 minus. O2 2 minus, it will be like what? Sigma, pi star 2px2 equal to pi star 2py2. So we can write the bond order is equal to half into 10 minus 8, which is equal to 2 by 2 equal to 1, and it is diamagnetic. Clear? Yes. I hope you understood this one. And coming to their stability, which will be more stable, the high bond order one, that is O2 plus, will be more stable than O2. Then we'll be having 1.5, that is O2 minus, than O2 2 minus. Write the significance of plus and minus sign showing representing the orbitals. That is nothing but electron wave. Okay, that is the electron wave that is showing the positive and negative sign, and the positive represent the crest of the electron wave and the negative sign represent the trough of the electron wave. Positive and negative electron waves are shown by that. Okay. Yes. Describe the hybridization in case of PCl5. Why are the axial bonds are longer compared to equatorial bonds? So coming to PCl5, we know the central atom is phosphorus, which is a 15th group element, and its outermost electronic configuration will be 3s2 3p3. Yes, that is the ground state electronic configuration. And in the excited state, we can draw it like 3s2 3p3. Yes, it will be like 1s here, and we'll be having D also. 1 2 3 4 5. Okay, 1. So in the ground state it was like this. I will show you. 1 2 3 4 and 5. So initially it was like this. Now what will happen? This bond will go to the D orbital, so it will be 1 2 3 4 like this. Okay, now each of the chlorine will come here, 2 3 4 5. That means here the hybridization is sp3d, where it is trigonal bipyramidal. What is that? Trigonal bipyramidal, and their shape will be like this. Okay, so their shape will be like this. Here it is the equatorial bonds. 3 equatorial bonds will be there and 2 axial bonds will be there. Okay, so 3 equatorial bonds and 2 axial bonds. So here you can see the axial bonds are suffering more repulsion from the equatorial bonds. That is why they are little weaker, and their bond length is higher. Bond length is higher compared to equatorial bonds, since they are suffering from more repulsion from the 3 equatorial bonds. That is why axial bonds are longer and weaker, we can say. Define hydrogen bond. We all know what hydrogen bond is. It is the bond formed between the hydrogen atom and highly electronegative atoms or elements like nitrogen, oxygen and fluorine, and the bond is stronger than van der Waals forces, and this bond is stronger than van der Waals force, we can say. Yes, that was a simple question, and I hope you understood the answer for this question. What is meant by the term bond order? Bond order is the number of bonds between 2 atoms in a compound. Number of bonds between 2 atoms in a bond. 2 atoms in a compound. Okay. So, and also calculate the bond order of N2, O2, O2 plus and O2 minus. For O2, we have already took that. We got it like 2 in the previous question that you can see. And O2 plus, we got it like 2.5. And O2 minus, we got it like 1.5. Now, let's look at for nitrogen. Nitrogen, we know what it is. Number of electrons, 14. So the order will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2 equal to pi 2p y2. 2, 4, 6, 8, 10, 12. Then we have sigma 2p z2. Yeah. So we will be having the bond order is equal to half into number of electrons in bonding minus number of electrons in anti-bonding. So it will be 2, 4, 6, 8, 10. 10 minus 2, 4. So it will be 6 by 2, which is equal to 3. So the bond order of nitrogen is 3 that we got. Yes. So I hope you understood the answer for this question as well. If you have any doubt, please let me know. So that's all about the NCERT exercises of the chapter Chemical Bonding and Molecular Structure. I hope you enjoyed the series, and I'll see you again with the thermodynamics chapters NCERT exercise problems. So yes, I'll see you there. Till then, bye bye.